universe is vast and mysterious, stretching beyond our wildest imaginations. It is a realm filled with countless stars, planets, and cosmic wonders that have fascinated humanity for centuries. But within its immensity lies an elegant order, a cosmic blueprint that governs the behavior of matter. This order is not random, but follows specific patterns and rules that scientists have worked tirelessly to uncover. This blueprint is the periodic table of elements, a masterpiece of scientific organization. It is a chart that categorizes all known elements in a way that highlights their similarities and differences, making it easier for us to understand their properties. It is a testament to the power of human curiosity and our quest to understand the world around us. The periodic table is not just a list of elements. It is a story of discovery, innovation, and the relentless pursuit of knowledge. In this exploration, we'll embark on a journey through the fascinating landscape of the periodic table, uncovering its secrets and unraveling the mysteries of the elements. But before we continue, I want you to hit the subscribe button and make sure you watch more of Taiwo Falana videos. Alright, you should know that each element has its own unique story, contributing to the grand tapestry of the universe. Imagine a vast library containing all the building blocks of the universe. Each book represents an element, and together they form the foundation of everything we see and experience. That's what the periodic table is. It's a comprehensive inventory of all known elements, arranged in a way that reveals their properties and relationships. It is a tool that scientists use to predict how elements will behave and interact with each other. It's a comprehensive inventory of all known elements, arranged in a way that reveals their properties and relationships. From hydrogen, the simplest and most abundant element, to the more complex and rare elements, each one plays a crucial role in the universe. From the air we breathe to the devices that power our lives, everything is made up of these fundamental ingredients. The elements are the building blocks of matter, and their interactions create the diverse materials and substances we encounter daily. By understanding the periodic table, we gain insights into the very fabric of reality. It allows us to comprehend the nature of chemical reactions, the formation of compounds, and the behavior of materials under different conditions. It's a key that unlocks the secrets of chemical reactions, material properties, and even the evolution of stars. The elements are not static. They are dynamic and constantly changing, driven by the forces of nature. So fasten your seatbelts as we embark on a thrilling adventure through the cosmos of chemistry. We will explore the origins of the elements, their discovery, and their impact on our world and beyond. Our journey begins with the pioneers who dared to organize the chaos of elements, their groundbreaking discoveries paving the way for modern chemistry. These early scientists laid the foundation for our understanding of the natural world, and their legacy continues to inspire new generations of researchers. The quest to understand the elements has captivated scientists for centuries. Early attempts to classify substances were rudimentary, often based on superficial observations. But as knowledge grew, so did the desire for a more systematic approach. In the 18th century, Antoine Lavoisier, a French chemist, made a groundbreaking contribution. He meticulously identified and listed the known elements of his time, laying the groundwork for a more organized understanding of matter. Then came Johann Wolfgang Dobereiner, a German chemist who noticed intriguing patterns in the properties of certain elements. He observed that elements with similar characteristics often came in groups of three, which he called triads. This discovery hinted at a deeper underlying order. Building on this foundation, John Newland, an English chemist, proposed the law of octaves. He noticed that when elements were arranged by atomic weight, every eighth element exhibited similar properties, much like musical octaves. While his idea had limitations, it further fueled the search for a comprehensive system. The stage was set for a revolution, and it arrived in the form of Dmitry Mendeleev, a Russian chemist with a vision. In 1869, he unveiled his masterpiece, the periodic table of elements. Mendeleev's table was revolutionary because it not only organized the known elements, but also predicted the existence and properties of elements yet to be discovered. Unlike his predecessors, Mendeleev arranged elements by atomic weight and their chemical properties. He boldly left gaps in his table, confidently predicting that these spaces would be filled by undiscovered elements. His predictions proved astonishingly accurate. The discovery of elements like gallium, scandium, and germanium, all fitting perfectly into Mendeleev's predicted slots, cemented his table's place in scientific history. It was a triumph of human ingenuity, demonstrating the power of observation, pattern recognition, and the audacity to embrace the unknown. However, Mendeleev's table wasn't perfect. There were some inconsistencies, and the underlying reason for the periodicity of elements remained a mystery. This is where Henry Moseley, an English physicist, stepped in. Section 4. Decoding the periodic table, a map of elements. The periodic table is not just a chart, it is a map that reveals the underlying order of the elements in our universe. Henry Moseley, through his groundbreaking work with X-rays, provided the missing piece of the puzzle. His research was pivotal in transforming our understanding of the elements. He discovered that each element possesses a unique atomic number, representing the number of protons in its nucleus. This was a significant breakthrough because it allowed scientists to identify elements more accurately. This revelation revolutionized our understanding of the periodic table. It provided a new way to organize the elements that was more precise and logical. Moseley's discovery led to the realization that arranging elements by atomic number, not just atomic weight, resolved the inconsistencies in Mendeleev's table. This was a monumental shift in the field of chemistry. The periodic law was refined. The properties of elements are a periodic function of their atomic numbers. This means that elements show a regular pattern in their properties when arranged by atomic number. With this newfound clarity, the periodic table transformed into a powerful predictive tool. Scientists could now predict the properties of elements that had not yet been discovered. It became clear that the arrangement of elements was not arbitrary, but reflected a fundamental order within the structure of atoms themselves. This order is what makes the periodic table such a valuable tool in science. The table is organized into rows called periods and columns called groups. Each period and group has its own significance in the layout of the table. Each period represents an increasing energy level within the atom, which means that as you move from one period to the next, the energy level of the electrons increases. While each group comprises elements with similar chemical behavior due to having the same number of valence electrons, the electrons in the outermost shell. This similarity in valence electrons explains why elements in the same group often react in similar ways. Section 5. Families of elements, sharing traits and quirks. In this section, we will explore the fascinating world of elemental families and how their shared traits and quirks define their chemical behaviors. Just like families share common traits, elements within the same group on the periodic table exhibit similar chemical behaviors. These similarities arise from their atomic structure, particularly the arrangement of their electrons. This is because they have the same number of valence electrons, which largely dictate how atoms interact with each other. Valence electrons are the outermost electrons of an atom and play a crucial role in chemical bonding and reactions. Let's meet some of these elemental families and understand their unique characteristics and behaviors. These are the alkali metals, the most reactive metals on the periodic table. They are eager to lose their single valence electron to achieve a stable electron configuration. When alkali metals react with water, they do so violently, producing hydrogen gas and a strong alkaline solution. This reaction is a vivid demonstration of their reactivity. Next, we have the alkaline earth metals. These elements are slightly less reactive than alkali metals, but still readily form compounds. They are commonly found in minerals and rocks, playing essential roles in various geological and biological processes. Moving on to the halogens, these are highly reactive nonmetals. They are eager to gain an electron to complete their outer shell, making them very reactive with metals and other elements. Halogens readily form salts when they react with metals. This process is fundamental in the formation of many compounds we encounter in daily life, such as table salt. Finally, we have the noble gases. These elements are the most stable and unreactive on the periodic table thanks to their full outer shell of electrons. Their stability makes them unique among the elements. Noble gases exist as gases under standard conditions and are often used in lighting and lasers due to their inert nature. Their applications are diverse, ranging from neon signs to advanced scientific equipment. These are just a few examples of the diverse families residing within the periodic table. Each group has its own story to tell, contributing to the rich tapestry of chemical knowledge. Each group possesses its own unique set of characteristics, making the table a treasure trove of chemical knowledge. Understanding these families helps us appreciate the complexity and beauty of the elements that make up our world. The periodic table, a chart that has fascinated scientists for centuries. It's a roadmap to the elements, each square representing a unique building block of matter. These elements are the building blocks of our universe, forming everything from the air we breathe to the stars in the sky. Today we journey into its heart to explore a fascinating group, the transition metals. These metals hold secrets that have intrigued chemists for generations. Occupying groups 3 through 12, these metals are not your average elements. They are the bridge between the main group elements and the inner transition metals. They possess unique properties that set them apart, such as variable oxidation states and the ability to form complex compounds. These properties stem from their partially filled d orbitals, electron clouds with intriguing shapes that influence their chemical behavior. This is where the transition happens, a shift from the predictable patterns of the main group elements to the more complex and versatile nature of the transition metals. Their unique characteristics make them indispensable in various industrial and biological processes. Electronegativity measures an atom's pull on shared electrons. Think of it as a tug of war. In the transition metals, electronegativity increases as we move across a period. Why? The increasing number of protons in the nucleus strengthens their grip on electrons. Down a group, electronegativity decreases. The outermost electrons are farther from the nucleus, weakening the attraction. Compared to the main group elements, transition metals generally have lower electronegativity. Electropositivity is the flip side of electronegativity. It's the tendency of an element to donate electrons, forming positive ions. Across a period, electropositivity decreases in transition metals. The increasing nuclear charge makes them less willing to share. However, down a group, electropositivity increases. The outermost electrons are farther away, making them easier to donate. This trend is more pronounced in transition metals compared to main group elements. Electron affinity is the energy change when an atom gains an electron. In transition metals, this trend is less predictable. The partially filled d orbitals create complex interactions. Generally, electron affinity decreases down a group. The added electron is entering a higher energy level, farther from the nucleus. Compared to main group elements, transition metals generally have lower electron affinities. Section 5, Ionic Radius, shrinking and growing. It's complicated. Understanding the ionic radius is crucial in chemistry. Ionic radius, the size of an ion, is another key property. It plays a significant role in determining the behavior and reactivity of elements. In transition metals, it decreases across a period. This trend is observed due to the increasing nuclear charge. This is due to the increasing nuclear charge pulling electrons closer. As the nuclear charge increases, the electrons are drawn in more tightly, reducing the ionic radius. Down a group, ionic radius increases. This is because new electron shells are added as you move down the group. The addition of electron shells outweighs the nuclear charge effect. Each new shell increases the distance between the nucleus and the outermost electrons. Remember, ions can be smaller or larger than their neutral counterparts, depending on whether they lose or gain electrons. Losing electrons results in a smaller ion, while gaining electrons makes the ion larger. Section 6, Ionization Energy, holding on to electrons. Tight. Ionization energy is the energy required to remove an electron from an atom. It generally increases across a period in transition metals. The increasing nuclear charge makes it harder to remove an electron. Down a group, ionization energy decreases. The outermost electrons are farther from the nucleus and easier to remove. Compared to s-block elements, transition metals have higher ionization energies. Section 7. Oxidation States, Masters of Disguise. Transition metals are known for their variable oxidation states. This means they can lose different numbers of electrons, forming ions with different charges. This ability stems from the small energy difference between the d and s orbitals. For example, iron commonly exists as Fe2+ and Fe3+. This versatility makes transition metals essential for many biological and industrial processes. Section 8. Magnetic properties from fridge magnets to powerful alloys. The arrangement of electrons in d orbitals gives rise to fascinating magnetic properties. Paramagnetism is the weak attraction to a magnetic field. Iron, cobalt, and nickel exhibit a stronger form, ferromagnetism. These elements have unpaired electrons with aligned spins, creating a permanent magnetic dipole. This property makes them crucial for applications like data storage and electric motors. Section 9. Color of compounds, a kaleidoscope of chemistry. In this section, we delve into the fascinating world of colors in chemistry, particularly focusing on transition metal compounds. Have you ever wondered why transition metal compounds are often so colorful? These vibrant hues are not just for show, they tell a deeper story about the nature of these compounds. The answer lies in the d orbitals. These unique orbitals in transition metals play a crucial role in determining the color of the compounds. When light shines on these compounds, electrons can jump between d orbitals, absorbing and emitting specific wavelengths of light. This interaction with light is what gives these compounds their distinctive colors. The color we see is the complementary color of the absorbed light. For instance, if a compound absorbs blue light, it will appear orange to our eyes. The presence of ligands, molecules attached to the metal ion, can further influence these colors. Different ligands can cause shifts in the absorption spectrum, leading to a variety of colors in transition metal compounds. Section 10. Conclusion. The enduring allure of transition metals. From the vibrant pigments in paints to the catalysts that drive chemical reactions, transition metals shape our world. Their unique properties, stemming from their partially filled d orbitals, make them essential for countless applications. Understanding their periodic trends unlocks a deeper appreciation for the elegance and complexity of the chemical world. Thanks for listening. Remember to subscribe to Taiwo Falana videos. Stay positive.